Hello, I'm Tom Langley, and welcome to Drunken Physics. Our topic today is one of the most compelling and interesting questions that stands in modern physics, and that is the problem of time. In classical mechanics, time is considered to be an exterior variable or parameter in the universe. It is always outside of the system. It is independent of the observer, the variable, the space, its velocity, its mass. It's independent of all variables. And it ticks away in the background like some universal clock. General relativity, which builds upon special relativity, takes time and it completely alters it and turns it into a relative concept. In special relativity, time is relative to the velocity of the observer, so that an object moving in relation to you at higher velocities experiences a slower time from your perspective. And then in general relativity, time becomes a variable again, which is still dependent on velocity as it was in special relativity. But now, in general relativity, time also becomes relative to the gravitational field, i.e. the mass of an object. As a matter of fact, the famous curvature of general relativity arises because of this time dilation. I'll actually give another lecture in which I explain that concept in greater detail. But the curvature of general relativity arises from the fact that time moves more slowly near mass, which causes the space to remain flat, but time to take on the famous dimpled shape as it compresses towards the central mass. Now, one of the most famous discoveries of general relativity is the fact that, one of the most famous discoveries of special relativity is the fact that for all massless signals that contain physical information, they must travel at the speed of light, and all objects which travel at the speed of light experience time durations instantaneously. Meaning that if I have a photon, and at the moment of its creation and the moment of its annihilation, no matter how long the photon is whizzing through space, the amount of time that's experienced by that photon is zero. Because all time is simultaneous for the photon, or all durations are zero for a photon. Now, one of the most famous discoveries of general relativity is the fact that it can be shown mathematically that for any two locations in space, there is at least one path called a light-like path that connects the two, such that a light wave that is released from point A, traveling through space and time, would reach point B. And so that path, which is traveled by a light wave, is called a light-like path. And as we recall from what we had just discussed earlier in special relativity, the space-time, or the time experienced by all photons traveling between 2 points is always zero. And so one of the discoveries of general relativity is that between any 2 points in space, we can always create a light-like path, meaning that I can always send a photon from point A to point B, and in space-time it will eventually get there. And for that photon, the total amount of time experienced is zero. Now, what this means is that I could select a location at the beginning of the universe, just after the Big Bang, and then I could wait and wait and wait until the end of time, until the end of the universe, even if it is infinitely far into the future, and I could select another point in space. And as we've learned earlier, I'm always able to connect any two locations in space by a path in space-time that is traveled by a photon. Meaning that if I pick a point at the beginning of the universe and a point at the end of the universe, I can connect them with a light wave. And that means that the total amount of time experienced by a photon, which is created at the moment of the Big Bang and then is annihilated at the instant or at the end of the universe, is zero. Meaning that from the perspective of that photon, the entire history of the universe is instantaneous. And let's think about that for a minute. That's pretty profound. That's pretty interesting that all of the billions and billions and billions of years of the universe's existence is experienced by this photon that we created at the dawn of time is experienced instantaneously. The total history of the universe happens simultaneously for this photon. Now, I feel it's necessary to stop for a moment and point out something, which is that even though time is relative, causality is not. Meaning that a photon that I've created as it's whizzing through space, if it experiences a series of events, that series of events is still going to happen in the order that the photon perceives it, because the order of events for all objects, regardless of mass, regardless of the relative time, is always the same. We call that causality, and in special and general relativity, causality is preserved. So now we find that we've got this description of the universe in general relativity in which I can easily describe the entire history of the universe as being instantaneous. And really, by a similar argument, I can also say that the entire volume of the universe is zero, or the entire distance traveled by that particle or by that photon is zero. But that's another issue. Now let's move to quantum mechanics. Quantum mechanics has a radically different view of what time is. In quantum mechanics, the way that we describe a particle is that a particle whizzing through space, all by itself, all by its lonesome, exists in something that we call a superposition of states, meaning that as it's going through space, it exists simultaneously in all possible states that are available to the particle. Now, the particle itself, I can't interact with it as it's whizzing through space. Instead, this particle exists in something that we call the wave function. And the wave function is simply a description of the probability of finding that particle in any given particular state. Now, the wave function will collapse whenever it interacts with another wave function, meaning conceptually that if I've got two particles whizzing through space, then when they collide with one another, we observe them and we find that the wave function collapses, and for that little instant the particles exchange some properties and start whizzing off in new directions as if they've just had a collision, whether it be elastic or inelastic. And once they start whizzing off in the new directions, they become wave functions again, and so cannot be perceived or observed until they have a new collision with some new particles. Well, in quantum mechanics, the only instants in time that make any sense are when two particles collide with one another. That is, when the wave function collapses and the particle takes on its particle nature and it becomes observable for a moment. It's only when that occurs that we can even define what we mean by an instant in time. We can say this collision is at this particular instant, and then as the wave function starts darting through the universe again, we can't label the location or the time of the wave functions as it's zipping through space until it has another collision. So in this way, the only way that we can define time in quantum mechanics is in terms of these individual and every one distinct instance in which the wave function collapses through some sort of interaction. Now, what this means is that the quantum mechanical description of time is that time is the sum of all the possible instants that are formed by the collapsing of all the different wave functions in the universe as they are interacting with one another. Now, this is radically different from the general relativistic view of what time is, in which time is continuous and smooth, it has no holes in it, but it is stretchy. I can make it longer or shorter, and there is at least one way I can look at the universe in which the entire history of the universe happens in a single instant. But then we move over to quantum mechanics, and quantum mechanics says, no. The only way that we can define time and duration in the universe is in terms of all of these billions and billions of multitudes of instants that are all separate and distinct. And here is the problem of time. We have these two descriptions of reality, both of which are extremely successful, but they don't play well together. And they both have not just radically different descriptions of what time is, but they have conceptually and mathematically opposed conception of what time is. So, thank you for joining me today, and next time I believe we will discuss the nature of time and gravity when it comes to curvature. Thank you.